Recording in progress.
Okay, good morning. Today we're going to start our 15 minutes student presentation. We have 7 speakers that will cover a variety of topics. And our first speaker of today is Felix Chahyadi that will talk about the realization of quantum switch with spatial photon state control via polarization. So without further ado, I would like to ask Felix to share his presentation.
Okay, sure. Let me share my screen first. Okay. Can you see my screen, sir? Excuse me.
It's processing at the moment.
Okay.
Yes.
Okay, so can you see it now?
May start.
Okay, so can I start? Or
yes.
Yeah. Okay, so hello, good morning, everyone, and good to see you. My name is Felix Hrd, and today I will present to you a very exciting topic, and it's called the realization of quantum switch with spatial photon state control via polarization. And so let's head to the first section. And here I'm going to discuss the superposition of order and also the purpose of this research. How do you send information through totally noisy channels? And this is the question that we are going to answer in this research. And so the answer actually lies in quantum phenomenon. And if you look at the screen, you will be familiar with the first picture. And it is the Young's double slit experiment. Here we have electrons that we shot through the slits, and the electrons will go through either one of them, and then it will produce an interference pattern on the screen. And this is what we call as a superposition of space. But we have another kind of superposition, which is the superposition of causal order. And basically, in this case, in some cases, we can send the information through the first channel before going into the second channel, and in some cases, we can send it through the second channel before going into the second channel. And this is one of the example of what we call as the superposition in time. And so what are we doing this for? Basically, in communication, when we send information through noisy channels, the communication will be less efficient since some of the information will be lost through the environment. And to fix that, we will need more resources because we want to do error correcting protocols. And if we are able to reduce the effects of the noise, then we can save on the resources and use it to send more information instead. And to understand how this research works, we'll need to get into the theory, the formalism for the quantum phenomenon, and also the relation to optics. For the start, we'll describe the quantum state for our qubit. So instead of using state factors, we will use density operators. The reason for that is because density operators can describe some properties that cannot be described by the state factor, for example, entanglement. And also, next, we are going to move to the quantum channel. Here we will define the quantum channel as the transformation function of the qubit. And basically, when it goes through the qubit, it will be transformed like this. And here is what we call as the general Pauli channel. Here we have the Pauli qubit, the Pauli matrices that will transform the qubit, and also the probability pi of doing so. And in this research, we will use the polarizing noise and the phasing noise. Basically, the general Pauli channel can be transformed like this. So here we have, for example, the value of P0 is 1 minus 3Q divided by 4. And also, yeah, basically, you get the idea. And with all of that done, we can then describe a special kind of quantum channel called quantum switch. And the reason for that name is because it works like switch. You have a control qubit that controls the operation. And if you look at the right side of the screen, you have the mathematical description of the quantum switch. And here we have the control qubit right here, the tensor product, and also the operations to the transmitted qubit. This tells you that if the switch is in the state 0, you will operate P first before you operate Q. And if you have 1 as the value, then you will operate Q first before you operate P. And the interesting part is if the control qubit is in a superposition between 0 and 1, then in order to describe that, we can use a general output state, which will look like this. And here we have the operator Kij that looks like this. And here we have on the control qubit and also the Pauli matrices that will work on the transmitted qubit. And by getting the output state, we can then describe the amount of information that can be transmitted by the channel using what we call as the high-level capacity. So if we have the general output state, we can use it, we can measure it using the von Neumann entropy in order to get the high-level capacity. And when we want to bring this into real experiments, we have to find the correspondence between the mathematical formulation and also the physical system. So in this case, we will encode the control qubit into light polarization, and we'll encode the transmitted qubit into the Hermite Gaussian modes. And what are the Hermite Gaussian modes? It is one of the example of the transverse photon state. Basically, we are going to look at the profile of the electric field. If we use a detector to measure them, we will be able to see these kinds of amplitude profiles. And in this experiment, we will be using the 0-1 state and also the 1-0 state. Next, we're going to talk about how the experiment setup will look like. So here's our setup. We have 2 polarizing beam splitter here and here, and we also have the channel A and B here and here. And as we can see here in figure 7, the channel A and B is actually made out of the set of lenses. This set of lenses will operate on the Hermite Gaussian states, and it will rotate them. Yeah, basically it will do a rotation operation to the Hermite Gaussian states. And here we also have C, which will act as the detector. And in this experiment, we will set the polarization of the laser to be diagonal, so reflected, and in some cases will be transmitted. And so in some cases we'll go through A first before getting back, and then getting into B before going to C. And in some other cases we will go through B first before going back and then getting into A and then into C. So what we are doing here is that we are using polarization to control the path of the input laser, and different paths will result in different modification of the shape. Next, to the result of the experiment. So from the experiment, we'll get the measurement results of the Stokes parameters, which will denote as S2. And we have all of the results for the combination of the Pauli matrices, and here is the theoretical value and also the experimental value. And as we can see here, the measurement value are not exactly 1 or -1. And the reason is because we have uncertainty within the rotation of the wave plates, and also the visibility of the light is also not ideal, and it's only around 85%. That's why in this case, you can see that the value is around 0.85. And from the measurement result, we can then calculate the Hall level capacity for the polarizing channel. Here, Q is the strength of the depolarizing channel, and also here is the value of the Hall level capacity. And here we have 3 lines. The black one is the ideal causal superposition. The orange one is the experiment, and also the blue one is in case without causal superposition. And the surprising thing is, as the strength of the polarizing channel goes up, the capacity actually goes back up, and it is surprising because we don't expect it to do that. And then we will try for another combination, namely the polarizing and also the phasing channel. And we can see that in the ideal case, we will retain the information. But because of the imperfections in our measurements, we have chi equals to 0.64 bits at Q equals 1. And then so to the conclusions. Firstly, we are able to realize quantum switch on photonic system with the polarization as the control, and also the Hermite Gaussian state as the transmitted qubit. And secondly, we have we achieve causal superposition, and we can use this to retain information that pass through noisy channels. And thank you very much for tuning in. If you are interested in this research, you can contact me via email, and have a nice day.
Okay, thank you, Felix. Question for Felix? Okay, in terms of the polarization, not properties, do we need to take care, do we need to consider a special step in providing the settings so that the result will be close to the value that we desired?
Sorry, can you repeat the question?
Okay, in terms of the polarization setting, do we need to make a specialized number or specialized setting so that the outcomes will be close to the number that we wanted?
I think so. In the case of polarization, I don't think we need to set. I don't think there is anything that we need to modify, because the only thing that we can do to the polarization is to modify value of the angle of the polarization, and it doesn't really affect our calculations. The one thing that affects our measurements are, for example, the visibility of the light, because we have like noise in the environment, and also the lenses can transform the photon quite a bit, and it is those imperfections are the ones that will affect the result of the measurements, and it is the one that we will need to modify instead of the initial polarization. Does that answer your question, sir?
Yes. I'm sorry, we're having a connection troubles in my office. If you could hear me. Can you hear my voice?
Wait a little bit.
Okay.
Yeah.
Okay.
I
Thank you
think
for
I can
your
hear you.
answer. Okay, thank you for your answer. And the follow-up question, I do have some follow-up question, but before that, I'm asked the audience, do we have another question for Felix?
I see. Okay.
So if there are no questions, my last question for Felix is that how many time that you spend to complete the calculation?
How many times?
How much time? How much time do you need to get the computation? Sorry, the calculation.
I don't think okay, so from the results, okay, so in order to get this kind of graph, we will need to so we can use the result from the S2 measurements in order to calculate the whole level capacity, and it doesn't really take much time because it's just some kind of a matrix operation. So basically, what we are doing are a lot of matrix calculations, and it doesn't really take much time to actually compute this. Does that answer your question, sir?
I can hear you. Okay, I can hear you, but the connection in my office is tremendously bad. So I'm sorry for the self-respect. Okay, thank you, Felix, for your description on your topic. And so that we can move on to the second presenter, which is Xrd Hrd.
Thank you very much, sir.
Takutnya yang buat aku tuh dari kakaknya kan bilang kayak ya reduknya ada orang yang jadi ya tapi itu tetap harus berusaha buat maksimal kita maksudnya kalau kita tuh terlalu ambisius buat manajer nominal motivasi kan ya motivasi juga buat orang lain ya.
Jihad, you can start whenever you're ready.
Good, sir. I'm setting my device.
Yes.
Is my screen visible, sir? Okay. Good morning, everyone.
Good morning.
Me, Xrd Hrd, Ramadan Bilkisti, 102 18027 will present my work, which talk about dust cleaning on solar panels using electrostatic principle and coating the solar panels with a transparent and conductive layer from aluminum doped zinc oxide. Okay, let's begin. A solar farm is large collection of photovoltaic solar panels that absorbs energy from the sun, convert it into electricity, and send that electricity to the power grid for distribution and consumption by customer like us. They operate as power plant, just like a natural gas power plant or other source of energy generation that have generate electricity. They they are decentralized and usually consist of the ground mount solar panels installed across large areas. Uh, as the thickness of the dust increase, hence the power output of solar panels also decrease exponentially. We can see in the figure 2. Uh, what should we do? So regular cleaning is very important to maintain the power output of solar panels. But cleaning solar panels currently is estimated to use about 10 million gallons of water per year, enough to supply drinking water for up to million people. What you will do? What you have to do is attempt to clean it without water, but it takes a lot to it takes a lot of effort and tends to cause irreversible surface scratch, which can also reduce the efficiency of solar panels. Again, reduce the solar panels. This temporary solution. So we truly need a non-contact way to remove dust from solar panels by not using water to make it sustainable. Method first, we must to determine the minimal electrostatic force to lift the dust particle. In this case, the dust particle we have similarly to silica to determine the threshold voltage. This is figure 5, initial concept of the dust removal mechanism. This is a equation that I used to this is the derivative of my calculate, and this is a diagram concept of the dust removal mechanism. Initial diagram, I'm sorry. This is finally schematic of the dust removal mechanism with azo coated glass inside on the top solar panel that have moving plates. This result, here we can see that as a coated glass display lower transmittance curve at smaller wavelengths because the amount of light that passed through the sample is less than that of the uncoated glass. This is figure 9 for power recovery from solar panel after dust removal for different dust particle size. After measuring the output power before and after cleaning solar panel for different size of dust particle, we get the following curve. Conclusion of my work is like transmittance of azo-coated glass and uncoated glass of the same thickness in visible spectrum measured using UV spectrometer. For most of the wavelength is visible spectrum from 450 until 750 nanometer. Both uncoated and azo-coated glasses have high transmission of 90% due to UV absorption. Azo-coated glass display low transmittance at smaller wavelengths. The power output after dust cleaning can be up to 350% better than before cleaning. Next, my presentation I close with the quotes from Mr. Hoirul Anwar, which said, saya terilhami oleh serial kartun Dragon Ball. Hoirul Anwar, inventor and the owner of FDM based technology patent. That's all from me. Thank you all. If you have any question, you can type in the Zoom. Thank you.
Okay, thank you. We have questions from the audience. Okay, we have Salma and Dara, and we should begin with Salma.
Okay, sir. I think it's a good idea to clean solar cell without water, but I want to know, with the tool set you use for dust cleaning, does it affect the charging process of the solar cell?
Can you repeat? I'm sorry.
Okay.
The question.
The main question is, does the tool set you use affect the charging process of the solar cell?
Okay. I will thank you, Salma, for the question. I will answer your question. Does the tool you use affect the charging process of the solar cell? There is no current flow between the top and bottom electrodes, and therefore no electricity power consumption. To power the appliance, a special separate battery unit can use in such a way that our dust removal mechanism does not draw power from the solar panel array. Can you understand my question?
Okay, so it doesn't affect the charging process.
Yes,
right?
Yes.
Okay, thank you, Fahri.
Okay, the next question comes from Dara.
Hello, Fahri. I want to
Hi.
ask you, when the power output given is small, why can there be dust?
Please lower.
When the power output given is small, why can there be dust?
It can be said that dust is an impurity that can block the sunlight. It should be noted that impurity is caused by a combination of absorption, reflection, and scattering of light by dust particle. This can obviously lead to a loss of output power. Maybe that's all from me. clear?
Thank you, Fahri.
Oh, okay. Thank you, Dara, for your question.
Okay, the next one is Anggun.
Okay, Fahri, I want to ask you, what if it rains? Can this tool be used after rain or not?
What if it rains? Can this tool be used after rain? Right?
Yes, Fahri.
Honestly, this tool cannot be used when the photovoltaic surface is wet. Therefore, this tool is suitable for use in areas with low rainfall. That cannot be used after rain. That's clear, Anggun. I'm sorry.
Okay, thank you for your answers, Fahri.
Thank you, Anggun, for your question.
Yes, and then the solar panel construction itself is usually done in an area where sunlight radiation is relatively constant. It means that
Yes.
we should choose an area in Earth that the cloud cover is minimum, and by that it doesn't create any chances for rain or for storm, etc., and so on. So therefore, usually the placement of the solar panel itself it is not on an area where the cloud concentration or the cloud cover is above a certain number. So, for example, the ambitious project of solar panel was done in the Sahara Desert, and Sahara Desert doesn't rain a lot, so that's why they made that ambitious project over there, even though they have problems, so on and so forth. But the plan is that to have a solar panel that is going to be work effectively and efficiently without any cloud cover or rain possibility on that area. Okay, thank you for Jihad. Thank you, Jihad, for your talk. And with that, we could move on to the next presenter, Ms. Miranda Sitompo.
Yes.
Okay.
Can you see my
Talking
screen?
about digital signal processing of radio wave spectrum from Timau Observatory area. Okay, time is yours.
Okay, good morning, everybody. Allow me to introduce myself. My name is Miranda Sitompo, and I'm here to present my research with the title Digital Signal Processing Based on Radio Wave Spectrum Measurement at Timau National Observatory Area, Kupang. In my presentation, there are 5 sections, namely introduction, basic theory, methodology, result and discussion, and finally, conclusion. The first is introduction. Mastery in space science is required by law number 2021 of 2013, namely research effort on space weather and environment, astrophysics, and space research, like ground-based observation facilities, such as the National Observatory. And second, based on the regulation of National Research and Innovation Agency number 5 of 2021, Research and Innovation Agency has tasks of carrying out technical tests of research, study, and application in field of space. And we do this research to prepare for the construction of a radio telescope system at the Timau National Observatory, Kupang. The second is basic theory. The first is horn antenna. Antenna is a device usually made of metal, as rod or wires, to transmit or receive radio waves. In other words, the antenna is a transitional structure between the free space and the waveguide. Horn antenna is a microwave antenna that we use in measuring the signal around the Timor National Observatory. And this horn antenna can cover the frequency range from 1680 to 18 gigahertz. The second is Fourier Transform. Fourier Transform is a mathematical operation calculation technique used to transform a time-based analog signal into frequency-based digital signal. Consists of discrete Fourier transform and phase Fourier transform. Discrete Fourier transform has the order n squared, and it takes a long time to complete the calculation if the data is very much. And to optimize the computational process, the FT can be modified with an algorithm that we often know as phase Fourier transform, or FFT. Phase Fourier transform is an algorithm to calculate the FT quickly and efficiently, and FFT reduce the order of the FT and square become n log n. And this is the example of signal in time domain, and we transform the signal from the time domain into a frequency domain using MATLAB. The third is methodology. This is the location of measurement at Timor National Observatory. Okay, in this picture we can see that code pin, latitude, and longitude. Code pin, it's mean the point of measurement. For example, R1N, it's mean radius 1 kilometer and north line. And in my research, I just processed 3 data, namely R1N, R2N, and R3N. Okay, the process is the first, the signal is measured use antenna horn, and then frequency signal measurement are carried out in 4 different measurement direction, namely EN is direction north line, and N north direction north line, SN south direction north line, and WN west direction north line, and at a radius of 1 kilometer until 3 kilometer. The frequency captured by this antenna is the frequency of 680 megahertz until 18 gigahertz, which is then divided into 7 parts, namely F1 until F7. After measuring, the data obtained is data in time domain, and we convert it to frequency domain with Fourier transform in MATLAB. And the data of the frequency and spectral amplitude values are separated for each measurement direction. Then the data from F1 until F7 are combined according to direction of measurement. And then we process the data with statistical calculation. For example, percentile and mean, because repeated measurement are carried out at several points. So we get 4 tables for each radius. And then we plot the data into a graph, and if the data have outlier data, we repair or adjust the data. After the data has been adjusted and the resulting graph is expected, then we perform statistical analysis. Okay, this is the result from my research. We can see the figure 5, the graph of measurement of signal north direction, north line at radius of 1 kilometer until 3 kilometers. From the graph, we can see that spectral amplitude is in the range of minus 45 decibels to minus 100 decibels. And from the measurement of 3 data with distance variation, we can see that the data obtained are similar, and they show that there's no material around the measurement point that interferes with the measurement at that distance. And we can see the confidence bound is 95%. This is the graph of measurement of the signal is direction north line at radius 1 until 3 kilometers, and we can see the spectral amplitude is in the range minus 14 decibel to 105 decibels. And we can see that the data obtained are similar. Okay, this is the measurement of the signal south direction and north line, and the spectral amplitude is in the range of 45 decibel to 100 decibel. Okay, this is the measurement of signal west direction north line, and from the graph we can see that the spectral amplitude is in the range of minus 65 decibel to minus 100 decibel. And from the measurement of three data with distance variation, it can be seen that the data obtained are similar, and this show that there's no material around the measurement point that interface with the measurement at a distance of 1 until 3 kilometers. And we can see that all four data have confidence bounds value is 95%. Okay, from the result of the data plot, then a regression is performed to find the gradient to see the response of temperature noise to its frequency. And the result of the trend line and line equation obtained in each graph we can see in table 1. Tabulate the equation of the line for each measurement. And we can see measurement point, there are 12, and the gradient is quite small, which is at part per billions, and this indicates that temperature noise response to frequency is small or not influenced. Okay, the last is conclusion. Okay, the first, based on the result of measurement and signal processing obtained around the location of Timor National Observatory using a Hz antenna, it was found that the value of the spectral amplitude at the measurement radius 1 kilometer until 3 kilometer with the same line and direction didn't differ significantly, which was in the range 40 to 100, minus 40 to minus 105 decibel. And this state that in the vicinity of measurement area, there's no material that interferes with electromagnetic signal from the atmosphere. And the second, based on the line equation of each measurement curve, a small gradient is obtained, which is on the order of part per billions. And this gradient shows that the effect of temperature on the signal measurement result around the Timor National Observatory area is not significant and can be ignored. And the third is confidence bound value is 95%. Okay, that's all my presentation today, and thank you so much for your attention. If there are some questions, I can try to answer it. Thank you.
Okay, thank you, Miranda. And by that, we have 3 questions. And the first question will be delivered by Sandy.
Hello, Miranda. Thank you for your presentation. I want to ask, why do you use horn antenna to take measurement?
Okay, why I use horn antenna to this measurement? Okay, we can see. Okay, first we need to know that this. Okay, wait. Okay, first we need to know that this signal measurement is carried out in a forest that is still rarely passed by human, and there are no routes for cars. There are trails. Then with a field like this, the horn antenna is used because the size and design from the horn antenna is simple and small size and have light weight, so it is easy to carry out everywhere. and this antenna is low cost to perform efficiently measurement. And this horn antenna can capture electromagnetic waves with a high frequency in the range of 680 megahertz until 18 gigahertz. And this antenna has a wide bandwidth and high gain, and we can adjust the performance gain according to our needs. Okay, I think it's my answer.
Okay, thank you, Miranda.
Okay, so the next one will be coming from Bunga.
Okay, thank you. My name is Bunga Denia. So I want to ask you a question. What does 95% of confidence bound mean in your data? Thank you.
Miranda, I think your mic.
Okay, I'm sorry.
Okay.
Okay, first we must know that what is the meaning of confidence bound. Confidence bound is a parameter used to determine the average accuracy of a sample. And when we make measurement and calculate the average value of the spectral amplitude, then we can estimate the actual value for the measurement data. And from the result of the data processing in my research, the confidence bound value is 95%. And it means that the average probability of the sample falling within that range in 95%. In other words, the maximum margin error, the maximum margin of error from the data is 5%.
Okay, thank you, Miranda.
Okay, so the error, what is the common error that we get from this kind of measurement?
This error can be come from the position when we do the measurement. It's cannot in Indonesian pas sesuai direction and line.
Oh, so okay, so if the signal is not on the same direction with the sensor, sometimes it can have a wrong measurement. Is that what you said? Is that what you mean?
Yes.
Okay. So it's more like, so the error more like is coming out from the equipments.
Okay, maybe there's errors from the equipment, example from the horn antenna, because yeah, the
Would be
antenna is
also coming out from rain or rain or dust or wind.
When the measurement is doing by when the not cloud, it's not rain, and the wind, I think it's not significantly give a
Okay, so in conclusion that rain and wind will not disturb too much with the measurement. So okay, thank you, Miranda. And with that, we can move on to the next speaker, which is Fahrisa Nurfadilia.
Maybe before I start, I want to apologize to everyone here if there is any sound disturbance because today I'm not feeling well, so my voice sounds weird. Okay, let's start. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. My name is Fahrisa Nurfadelia Bahraini, and today I will present my research talk about multi-technique for the characterization of the sidewall of hydrocarbon reservoir rocks. I'm from Department of Physics, Bandung Institute of Technology. For today's agenda, I will discuss about the introduction, theory, the characterization method, result, and this discussion, and the last is the conclusion. For the first is introduction. In human life, oil and gas are a non-renewable natural resource. This natural resource provides many benefits that human needs in their daily activities. Oil and gas are contained beneath the Earth's surface, which can be processed for use. There have been technological development and optimization of oil resource extraction in recent years. One of the methods is enhanced oil recovery method, or EOR method. Optimization of the EOR method can be done by characterizing the rock in hydrocarbon reservoir area. As you can see in the pictures on the slide, in a field, if we take a block of sandstone as a reservoir scale, we can characterize it to see it on a microscopic scale. So we can study about the physical and chemical properties of the rocks that made up the field. The next is characterization method. In this research, several different techniques will be used to characterize the sidewall core sample of hydrocarbon reservoir rocks. The first is microcomputed tomography, or micro-CT. The second is X-ray diffraction, or Xrd, and the last is scanning electron microscopy, or SEM. What are minerals and rocks? Minerals are substances that occur naturally and have physical and chemical properties relate to their structure and composition. If we have many mineral composed, we can have a rock. So, rock is a collection of minerals arranged in a single unit to form a large size. There are three types of rocks. The first is igneous rocks. And the second is metamorphic rocks, and the last is sedimentary rocks. Next, about rock characteristic. The first is porosity. Porosity is the empty space that is created throughout the layers between the grains that made up the field. In mathematically, the porosity is expressed as follows in the slide. The porosity, when we looking at the picture on the slide, there is an effective porosity or interconnected porosity, and also there is an isolated porosity or non-effective porosity. The next rock characteristics is clay mineral. Clay mineral is a type of soft natural rocks in the form of fine grains with diameter less than 0.005 millimeters. And clay minerals are a characteristic of minerals on Earth that have varying amounts of ions, and the physical and chemical properties of rocks can be caused by the presence of clay minerals in them. Next is what research techniques are used. The first is microcomputed tomography, as I said. Micro-CT is one of the digital rock physics techniques. This method is a computer-based digital image simulation. So the characteristics such as porosity, rock permeability can be estimated. This is an illustration of how micro-CT works. There is an X-ray tube that emits an X-ray beam to the sample, and there is a sample specimen that can rotate the sample 360 degrees, and a detector that will record the signal that is sent to the computer, and processed into a digital image. Computers are also used to control the tube and the machine of the specimen. Next, about the Xrd. Xrd used to analyze the structure of a crystalline, semi-crystalline, and non-crystalline material of a sample. Xrd utilizes the principle of diffraction and the high energy of X-rays. These techniques relate to the characteristic of the electron paths in an atom. This is an illustration for Xrd. There is an X-ray tube that shoots the X-ray into the sample so that it becomes unstable and must release energy again to achieve stability. So the detector will record the energy as a signal and obtain the sample mineral phase. Next is about SEM. SEM is the result of the development of the light or of optic microscope. SEM utilizes an electron beam and obtain a digital image of the surface morphology of the sample. There are 3 detectors in this method, namely backscatter electron detector, secondary electron detector, and X-ray detector. X-ray detector will provide information about the elements contained in the sample. Research process flowchart. This is the flow diagram of the research process. First, the sample must be prepared. Do the process using 3 methods, microcity, Xrd, and SEM, and then collect all data from each method, analysis of this data, draw conclusion, and research is complete. So next is the research results. For microcity, we get the sample image display in 2D and 3D. Figure A is a 2-dimensional view of the sample image. It can be small grains. It can be seen that the sample consists with small grains that accumulated and form a larger or a single unit. Therefore, there are pores between the grains. In figure B is a 3-dimensional view of the sample image. It can be seen that the small grains dominate the entire area of the sample. So there's possibility that the sample belongs to the type of sandstone. It's sedimentary rocks. However, if you look at the red circle in figure B, there are area with brighter contrast than the other areas. So this can be explored further by adjusting the opacity. This will select the area according to the brightness level. In figure C shows an area with a higher brightness level with opacity change, which means it has a high density. As it turned out, there were many areas of large grain size at the top of the sample image. In microcity, analysis was also carried out to determine the effective porosity value of the sample. The software used is called CT Analyzer. In the sample image, FOI or volume of interest is cut because there are parts with non-uniform contrast, such as in the top and bottom areas of the sample image, as you can see in illustration of FOI cutting in this slide. And the sample image is cut into blue blocks in the illustration. One of the most influential process in CT Analyzer software is the selection of the threshold value. This threshold we choose the threshold value because at the threshold adjustment, the sample portion will be divided into solids and pores before being converted into a binary image. The effective porosity we get is 30.412%. with an error of 18.19%. This error can be caused by point cutting before. So not all areas of sample are analyzed and differences in the capability or resolution of the laboratory measurement and CTAN calculations. In addition, porosity calculations are also carried out on the sub-VOE, which is a smaller area than a sample image. It is found that the porosity value is still quite uniform in each area. Next is Xrd results. We get the graph of the intensity with 2 theta. It can be seen that there are intensity peaks in the graph that can provide the type of mineral phase of the sample based on Xrd database used. There were 6 mineral phase detected, namely quartz, cristobalite, sulfite, dictite, franginite, and anorthoclase. Each phase has a formula and a weight ratio, but weight ratios do not exist for sulfite and franginite due to the limitations in the Xrd database. Next is SEM results. At a magnification 100 times, it can be seen that the surface of the powder sample under examination consists of a number of solids in the form of grains. This fact is quite obvious and can be related to the microcity results that are true if the sample consists of grains. At magnification 1000 times and further shows more deeply how morphology of these grains. The shapes looks like thin sheets that are arranged. If it is associated with the type of element contained in the Xrd results and comparing them with several same results in other researches, it is known that the type of clay minerals in the sample is kaolinite. However, to be sure, it still needs to be studied further. The last is conclusion. We know that the sample consists of small grains of rocks that are dominant and form a single unit so as to produce a larger size. The grains provide pore space and the porosity value is 30.412% and is quite uniform in some areas. There were 6 mineral phases detected, namely quartz, cristobalite, sulfite, dictite, franginite, and anorthoclase. The most probable type of clay mineral is kaolinite, and the homogeneity of the sample is not yet known, so that it requires further research. I think that's all. Thank you for your attention. And if you have any question, please ask me. Thank you.
Okay, thank you, Arisa. Questions from the audience. Okay, we have Bunga and Miranda. Okay, but before that, I would like to ask Farisa about where do you get the sample? Do you know where is the location of the rock is taken?
About the location, I don't know the specific location. I just my lecturers just give me the code sample and the title is Sadewa 4 and Sadewa 5. Actually, I have two sample, but from this presentation, I will just show you one sample.
Oh, so your advisor only gave you the image, not the sample itself. The rock sample.
I do get the samples, but for the image.
But you don't know where the rock is taken from. You don't know the location where the rock is. Okay.
Yes, sir.
Okay,
I
gotcha.
don't know.
Okay, Bunga.
Okay, thank you, Marisa. I'm Bunga, so I want to ask you, if I'm not mistaken, you say that to know the homogeneity of the sample, further research is needed. So why do you say that? Can you explain it? Thank you.
Okay. Sorry. Well, the homogeneity of this. I write the homogeneity of the sample is not yet known, so there is request for the research. Well, I need further researches because, as I said before, we know that there are quite larger grains in some areas at the top of the sample, and this can lead to visually that the sample is heterogeneous. But if we consider the porosity values of each subpoint, the values are quite uniform in each area and closer to the homogeneity properties. So because these results are quite contradictory, it's still necessary to do the research. Maybe we can do more subpoint to analyze the porosity value. I think that's it.
Oh, okay. Thank you, Farisa, for the explanation.
Thank you.
Okay, so the next question comes from Miranda.
Okay, good morning. Here I want to ask you, Nurfa, you compare the laboratory result with the result of microcity, and the results are different. Why does that happen?
About the error.
Yes, error.
Okay. As I said before, this error can be caused by POV cutting in CT analyzer process, so that not all areas of the sample are analyzed, such as from the laboratory measurement. And actually, the sample has been studied by a team of lecturers and relate to the laboratory measurements. And I was given some parameter value. One of them is porosity. And this value could be compared with the result of microcity about the porosity, and error of 18.19, I think 18.19%. It's because the capability or the resolution of laboratory measurement and the CT analyzer calculation have a different capability or have different resolution. So the CT analyzer calculation will not be higher than the lab measurement results. I think that's it. Miranda.
Okay, thank you for your answer.
Okay, I would like to thank all of the questions from the audience, and also thank Farisa for the topic. And with that, we can move on to the next presenter, Adrio Rifan, talking about the application of gallium phosphide as photovoltaic cell.
Yes. Is my voice clear?
Yes.
Can you see my screen?
Yeah. You may start your presentation.
Okay. And let me, good morning, everyone. Let me reintroduce myself again. My name is Xrd Hrd. I am a member of Physics of Photonics and Magnetic Research Group, Physics Department, Bandung Institute of Technology. Today, I want to present to you about the application of gallium phosphide as photovoltaic cell. Okay, this is the outline of this presentation. We start from the introduction and basic theory relate to this research and the methods that used in this research. Also, the results that I get from this research and the conclusion from this research. Okay, we start from introduction. We all we already know about what is electricity because we also use it in our daily life. Even now we use it as the power for our Zoom meeting, and we also knew that most of the electricity we use right now is produced from fossil fuel that is not an renewable energy source that will run out eventually if we just use it without without using the other energy source and but don't worry because there is alternative and renewable energy in everywhere in our daily life, and one of them is solar energy. And one of the method to create the electricity through the solar from the solar energy is the photovoltaic method. And what material do we need to use the solar energy? The 3-5 Bachelor and Xrd structure have a promising have become a promising material for the solar cell. And one of them is gallium phosphide that have an interesting feature for a high band gap solar cell. But beside of the solar cell, gallium phosphide also can be used in many applications such as LED and also photo cell. And one of the most promising solar cell that already been discovered right now is third generation thin film solar cell that is expected to achieve 35% of efficiency with the use of multi-junction cell. And for the photovoltaic cell itself, gallium phosphide can be used as the coating of the solar cell or the solar cell material itself. And in this research, this research aiming to get the best fit parameter for the photovoltaic junction based on gallium phosphide. And the figure 1 is showing the structure of the baseline gallium phosphide photovoltaic cell that used in this research. Okay, we go to the basic theory. I already mentioned about photovoltaic cell, but what is photovoltaic cell? The photovoltaic cell is the electricity through the photovoltaic effect, and the PV cell itself consists of many layers such as semiconductor layer of conducting material, and anti-reflection coating. The semiconductor layer is the layer that will generate the electricity through the photovoltaic effect, and the layer of conducting material is the layer that will collect the electricity produced from the semiconductor layer, and the anti-reflection coating is used to reduce the amount of solar radiation that reflected back from the surface of the cell. And in the figure 2, is showing you the most common structure of the photovoltaic cell, with the semiconductor layer is called specially treated semiconductor material in this, and the front contact and back contact is referred to the layer of conducting material. Okay. I also already mentioned that the photovoltaic cell generates electricity through the effect called photovoltaic effect. But what is photovoltaic effect? The photovoltaic effect is occur when the P-type and N-type semiconductor is formed together, join together to forming the PN junction, and the PN junction will generate the electric field that will allow the electron to move to the N-type and negative N-type, and the whole move to the positive P-type. And when the light incident to the cell, to the to the photovoltaic cell, the photon will give energy into the electron that will make the electron to be excited into the higher energy state called conduction band. And electron in the conduction band can move freely, and this motion of the electron that will create the electricity that will be collected by the layer of conducting material in the photovoltaic cell. Okay. And the method that used in this research is divided into two methods, that is the characterization and the simulation. For the device characterization, we'll characterize the light response with the use of xenon lamp AM 1.5 filter and also the internal quantum efficiency of the cell. And for the simulation, will be carried out in ADAPT-F or diffusion based on solar cell simulator. And this is the result of the characterization of the cell. For the figure 3, A is the light response of the gallium phosphide cell, and the figure 3B is the dark response of the gallium phosphide cell. And the from the measure light response, we also get the open circuit voltage and short circuit current, respectively 1.53 volt and 0.959 milliampere per centimeter squared, with the fill factor of 0.8 and efficiency of the cell is 1.17%. Okay, this is the initial internal quantum efficiency of gallium phosphide cell that we did use in this research. And for the simulation result, we get the best fit parameters of this type of cell is for the end contact with thickness of 150 Armstrong and active layer with thickness of 0.5 micrometer, and P active layer for thickness 4.5 micrometer, and P buffer layer is 1 micrometer. Thickness is 1 micrometer with the dopant concentration listed in the table 2. And for the simulation itself, after we get the best fit parameter, we also simulate for some condition, that is for without anti-reflection coating, like this, like the structure that used in this research, also with the anti-reflection coating and with the improved front surface and p-type also with the anti-reflection coating. And from the simulation, we get the interesting result that the anti-reflection coating increase the efficiency approximately 2 times higher without the anti-reflection coating. And after the front surface and p-type active layer is improved, we get approximately 4 times efficiency 4 times higher than the one without improved front surface and p-type. So from that result, we also get the conclusion of this research that the best fit parameter was conducted successfully and also already listed in table 2. And from the simulation, we also get the p-type material quality is affecting cell efficiency, that we knew that improving the p-type material will increasing the cell efficiency. And also the anti-reflection coating will enhance the cell's efficiency greatly without the one with no anti-reflection coating. Okay, that's the end of my presentation. If you have any question, feel free to ask me. And thank you for your attention. Yeah, thank you.
Okay, thank you, Adrio. Do we have questions from the audience? Okay, we have Amanda and Melissa. Okay, Amanda.
Yeah. Okay, thank you, Adria, for your presentation. In introduction, you mentioned that the third generation of thin film can reach efficiency 35% of efficiency, right? Yes. And could this photovoltaic from gallium phosphide reach the efficiency higher than 35%?
Okay, thank you for your wonderful question, Amanda. If for this gallium phosphide based cell have efficiency higher than 35%, I don't really know, but for the efficiency approximately 35%, maybe it can, but mostly it can, but it does not carry it out in this research. But if we want to, but if the further investigation is carried out, maybe it can be done with the improving the p-type material, or maybe the changing the doping of the p-type active or p-type buffer layer in this gallium phosphide in this cell. So yeah, if we get the better material for doping in this p-type active or p-type buffer, maybe we can get the 35% efficiency, but also with the anti-reflection coating, because in this research I don't use the anti-reflection coating in the cell that use in this research. Okay, is that answering your question?
Okay, thank you, Adria.
Okay, and the next question will be coming from Melissa.
Okay, thank you, Adria, for the explanation of your topic. I'm sorry if my question is maybe too basic or I miss the explanation, but I still don't understand about the parameters you mentioned earlier about the measured light response, how we concluded from the curve we get.
Oh, okay. This table 1, I think. Melissa.
Yeah.
Okay. For in the table 1, we get the result from we get the value from the IV curve of light response of gallium phosphide cell. For the open circuit voltage, we get it from the maximum voltage that occur when the net charge is 0, and net charge of the cell is 0. Or in this figure, we can see the maximum voltage when the current is 0 is approximately 1.53 in the curve. And also the short circuit current is measured when the maximum is the maximum current when the voltage of the cell is 0. I think it's kebalikan of the VOC, or in this curve we can also get it. When the voltage is 0 is approximately 0.959, and the fill factor itself is the ratio of area of the power, the max power output in the cell, or Vmax and Emax, per the area of the short circuit current times open circuit voltage. Yeah, I think that's all. I hope it can be.
Okay, I get the point. Thank you, Adrio.
Thank you.
Okay, with that answer, we could move on to the next presenter. Okay, thank you, Adrio.
Thank you, sir.
Will be ready now, Satrio. Okay, if Radinal is not available today, we could move on to Mulia.
Yes,
to
sir.
Jiastuti.
Okay. Okay, please wait.
Okay, you may start your presentation.
Yes, okay. Bismillahirrahmanirrahim. Good morning, everyone. My name is Mulia Sujastuti Wahyono. I'm from Physics Magnetism. Excuse me.
Good morning.
Oh yes. My name is Mulia Sujastuti Wahyono. I'm from Physics of Magnetism and Photonics Research Divisions, Bandung Institute of Technology. Today, I will presenting about my research, the optical characteristic of nanoparticle aggregates. Okay, there is the outline of this research. First of all, we must know the background and the purpose of this research, and then the theory. It will explain it about the electric field and magnetic field integral equation, and then the methods. I will explain it about surface integral equation methods, and then we can find the result and discussion for this research. And the last is the conclusion of this research. Okay, first of all, the background and research. Okay. At the end of this decade, nanoparticle technology to manipulate light beams has become one of the topics of study that continue to develop in the science and technology. The one is nanoplasmonics structure, where the resonance response is seen as a reaction in the external optical field. Besides that, this structure can be used in the chemical sensing, biosensing, waveguides, and metamaterials. In making this nanosystem, there are many challenges, such as manufacturing process and selecting suitable materials. The electron material, such as silicon, is also widely used to substitute for metal materials. It has several advantages, such as low dissipation power and ability to excite magnetic moments in the visible light range. The electric structure has been utilized as a nano antenna and two-dimensional metamaterials designs to evoke several phenomena such as induced transparency, light beam collimation, and cloaking effect with lattice arrangement. So in this research, there are many problems. When the scattering object is irradiated by electromagnetic wave, it can be in the form of a field wave, dipole radiation, or a laser beam. The wave will be scattered outward and absorbed into the object. So in this research, we analyze the scattering response of multiple scattering system in the form of silicon aggregates, in this case of far-field observation. The scattering wave is the one of the optical response that can be analyzed experimentally and computationally. Scattering wave can be obtained analytically by meteory for scatter with spherical geometry. However, the scattering with arbitrary geometry, we must require scattering multiple electromagnetic computational methods. And so for this research purpose, we must know about surface integral equation. What is surface integral equation? Surface integral equation is derived from Maxwell equation through Green's theory of function, where the surface integral equation has a good computational results for any solid scattering structure with a wide range of the permittivity. So we use the surface integral equation. We can determine the scattering characteristic of the trimmer silicon aggregate scatter using the surface integral equation method. Okay, that is the theory of this research. We're starting by from Maxwell equation on free charge particle. That is the Maxwell equation where D is this displacement field, E is electric field, and B is magnetic field, and H is auxiliary field. And we look at the figure 3. That is the geometry of the electromagnetic scattering problem, where the region 1 is the background and the region 2 is the scatterer object. In the scatter object, we have the G and M, where the G and M is the surface current densities, where the G is for electric field and M is magnetic field. Each region has a volume. V1 for region 1, the background, and V2 is for scatter object. And each region has a normal vector, and one is for region 1, the background, and 2 is for region 2. And they are perpendicular to a scatter object. Okay, so we must know about the electric field integral equation and magnetic field integral equation. The equation of the total electric field is obtained, which is the sum of the incident field and scattering field as given in the following equation, where the total electric field in the both region can be obtained if the diadic green tensor, the G gamma, and the surface current densities, Gs and Ms, are known, where the diadic green tensor can be obtained by transforming it into scalar Green function, and the surface current densities we can obtain by methods of moments. For total magnetic field, using the analogous derivation starting by differential Ampere's law. So we get the magnetic field integral equation as we write in the equation number 2. So as I mentioned before, electric field integral equation and magnetic field integral equation can be solved if the surface current densities are known. The method to solve this called by a method of moments, where a set of set expansion function and testing procedure are developed to use derive the elements of the moment matrix, where the A matrix, we must know about a PMCWT matrix, where the PMCWT matrix combine electric field and magnetic field, where the electric field we putting in the top half of the matrix A, and the magnetic field we put in the bottom half of the matrix A matrix. And the B matrix is the basis function for each field. That is for electric field, and that is for magnetic field. So we can find the current densities G GMN, where the Fn is a Rao-Wilton-Gleason basis function is for the triangular mass that I use in this research for the scatter object. And if we can find the GMN, we can substitute to equation 1 and 2, where is the electric field and magnetic field integral equation. Okay, there is the dyadic green tensor. The dyadic green tensor in homogeneous medium can be derived from the green scalar function. Yeah, there is the dyadic green tensor. If we know the dyadic green tensor, we can find the D and K matrix in the A matrix, and then we can substitute D and K in the A matrix, and can we find the GMN, the surface current densities. And if we get the surface current densities, we substitute again to the equation number 1 and 2, and can we find a complete electric field and magnetic field integral equation. Okay, there is the methods that I use in this research. Okay, we're starting by the calculation of the scattering field and magnetic field on the aggregate structure using surface integral equation methods. We can find the scattering field. Okay, the scattering field, we decomposition by multiple expansion methods. Again, we can find the coefficient of scattering. The coefficient of scattering we processing, and we can find scattering cross-section and multiple moment. And then we can calculate of the percentage contribution of scattering field decomposition. And then we can compare and analyze of scattering response of aggregate structure with various types. Okay, there is the result and discussion. Okay. Okay, first of all, the direction of the polarization that I use this research, the electric field in the horizontal order, and the K factor means that the propagation of wave in the vertical order. When we view from multiple decomposition, the default field has a dominant contribution, red line, in the monomer and folded folded trimmer ball system. Okay, scattering cross-section for monomer and folded trimmer ball system has a different profile. The dipole field has a 2 peaks in the folded system, and the system has a different resonance value. A resonance shift occur around 4,060 nanometers, caused by the different value of atomic polarizability, where the value comes from the significant dipole moment. Okay, the last is the conclusion of this research. Okay, the first, dipole field has a dominant contribution in the monomer and folded trimmer ball system, and then the scattering cross-section in the monomer and folded trimmer ball system has a different profile, where in the folded trimmer ball system has a 2 peaks dipole, and a resonance shift caused by a different value of atomic polarizability. If you interested with this research, please contact me. Have a nice day and thank you. Any question?
Okay, the first question for Mulia will be coming out from Salma.
Oh, yes. Okay, thank you, sir. And thank you, Mulia, for your presentation. I want to ask you about your choice in structure why did you choose a structure with this shape?
Okay, nice question from Salma. Thank you, Salma. Okay. When nanoparticle is dropped on the substrate, it can be formed a linear, the left figure like this, and a folded structure. And so if we know the scattering cross-section profile in its structure, we can predict the shape of the nanoparticle structure without any doing experiment. Can you understand what I mean?
Okay. Sorry. So you choose this because it's suitable for computational, isn't it?
Yes, the
Okay.
simulation and I'm not doing the experiment.
Okay. Thank you, Mom.
Okay, and then the next question is coming from Denny.
Okay, thank you for the opportunities to ask the presenter. What will we get from the result of the research for our daily life or another research? Thank you.
Okay, thank you, Dennis. That's a good question. There are several physical phenomena cannot be explained in this research, such as example, there is only the contribution of dipole moment is more dominant and cannot always generate other multiple moment. However, scattering in the system of more than two scatterers are interesting to be learned. Maybe allow for more interesting phenomena that can be observed and more application that can be applied. For example, for chemical sensing and biosensing to detect a cancer cell in the body. Yes.
Okay.
Okay, thank you. I think clear.
And then the next question will be coming up from Amanda.
Okay, thank you, sir, and thank you, Mulia, for your presentation. I want to ask about the method that you use in this research. Have you ever tried to compare the method that you use in this research with the other methods, and what's the difference?
Okay. Thank you, Amanda. Nice question. Yes, I have compared it with, did you know FDTD methods? Yeah, the results obtained are more accurate with FDTD. Why? Because there is this method that I use, surface integral equation, is only good for one nanoparticle. But in this research, I use three ball system. Yeah. But the peaks are the same, but it's not accurate with surface integral equation. That is more be accurate with FDTD, and it's also my challenging in my research to measure it accuracy more than the one structure. Yeah.
Okay. Thank you, Mulia.
Yeah. Yes.
Well, I'm not sure if finite difference could answer the problem that is arise from the questions, because finite difference itself is a numerical method, right? And every numerical method has their own errors, especially numerical errors. But maybe if you could tune in the boundary condition, and then the way that you place the three object on the grid, then probably and also the could you do you know what is the frequency that is used for this experiment? I mean, the choice of frequency and the size will determine whether your finite difference will be successful or not.
Okay. Honestly, I didn't know exactly about the frequency, but this I use in the surface integral equation. I'm not using perfect match layer boundary condition. I'm not. Yeah. So that the accuracy is not good. More than not good. Yeah, that's for good in the FTTD.
Okay. Okay, but yeah, because if you have the correct lambda, if you have if you have the most optimum lambda in finite difference, it may resolute the object better. But if the lambda is too long, it means that you cannot get anything from it. Okay, thank you, Malia. Do we have Radina in the classroom? Okay, Muhammad Radina Satrio Nugroho. Okay, going once, going twice, going thrice. Okay, if there are no Radina, it means that we are at the end of our session. The third session of 15 minutes student presentation. We'll continue our final part of student presentation on Thursday, and I think there will be 7 or 8 presenters for that session. So stay tuned on Thursday for our final session. And in the final session also, I'm just gonna remind everybody that all of you need to send or upload the final version of your paper, so that during holiday you're just concentrating on celebrating the holiday, or do beneficial activities with the holiday, and then come back and then you come back with the poster presentation after the holiday is ending. Okay, thank you all. We'll meet you again on Thursday. Let me stop the recording.